Hey Alge, here is the second day of notes for the 9.1 chapter. So we're going to keep talking about the exponential growth and decay. So we're going to look at these four functions and we're going to try to determine if they represent exponential growth or exponential decay, and then why or why not. So this first one, I have 0.5 times 2 raised to the x power. I notice that my b is a 2, and I know that b greater than 1 means I am going to have exponential growth. So this one's going to have growth. Don't get it confused with the a out in front. That would be a fraction. Similar to our next one, you'll notice here b is 0.5, and when b is less than 1, that means we're going to have decay, and that's when it's between 0 and 1. Remember, if it's negative, it's just going to flip it over. So this one is going to be decay. All right, this next one is a 2, so b is equal to 2 and b is greater than 1. So you would think this would be growth. However, because we have a negative a, that means it's going to flip it down and it's going to decrease. And we don't say that this is exponential growth or decay. We're actually going to say that this one is neither. Because it follows an exponential growth pattern in the negative direction, it's really hard to say that something grows negatively. So that one is neither. All right, this last one then is a little tricky because we have a negative exponent. Now, if we switch this, if we rewrite as f of x equals 2 times 1/2 to the x, so that we have taken that negative and we've distributed it into the 2 here and turned it into a fraction, you'll notice that b is less than 1, making this a decay function. All right, now we're going to move into sketching the graphs. So I'm going to do this in 2 different colors so you can see it, but I'm going to put it all on the same graph. So the easiest way to sketch exponentials is just to make a table. And I know some of you are still kind of uncomfortable with that. It's okay, we're going to work through it together. So in my x, my y categories, I'm just going to start plugging in numbers. So if I plug in -1 in my x, I get 4 to the -1. If you need to see that on a calculator, you don't just automatically know it. 4 raised to -1 is the same thing as flipping 4 into the denominator, so it's going to be 1/4. And then we have to multiply it by this 1/2. 1/4 times 1/2 is going to be 1/8. When I plug in 0, I get 4 raised to the 0 power, which is just 1, times 1/2 is 1/2. When I plug in 1, I get 2. When I plug in 2, I get 8. And this pattern makes sense to me because if I look back here at my b, I notice that it's a 4, which is greater than 1, making this a growth function. So let's go over to our graph right away before we move on to the next one. And we should see that when we plot these points, we're going to get a growth function. So I'm going to start at about -1. I know it's hard to see on this graph. If you want to do it on graph paper, you can also do that. We're going to go up to positive 1/8. That's really hard to see because it's really close to the axis, but that's okay. When I go over to 0, I'm going to go up to 1/2. Also kind of hard to see, but we're going to keep going with it. When I move over to 1, I go up 1, 2 full dots. When I move all the way over to 2, I'm going to go up 1, 2, 3, 4, 5, 6, 7, 8. And it's okay if you need to put your dots on there if you want to sketch those lines so you can see it. But essentially what you're going to see when we connect these, carefully, is we should see something that looks like this. We should see growth in the positive direction. All right, I'm going to jump over to my other one now. This one, before I even make the table, I'm going to notice that a 1/2 in my b position means this is going to be a decaying function. But to graph it, the method is going to stay the same. I'm still going to plug in my x and y table here. When I plug in -1, this is a little tricky, but I always just remember to grab my calculator if I'm really unsure. I'm going to be putting 0.5 to the -1. Let's see what that does. Remember, because it's 1 over 2, when we have a negative exponent, it flips it. So my 2 that was in the denominator now goes to the numerator. So I have 2. Keep going with this. When I plug in 0, I get 1. 1 times 4 is 4. Oops, I forgot to multiply this last one by 4. Haha. This is actually 8, because once we have that 2, we have to multiply by the 4. Thanks for bearing with my mistakes. When I plug in 1, I'm going to get a 2. And when I plug in 2, I'm going to get a 1. So let's go ahead and graph this now. I'm going to go to -1. I notice I get to start all the way up here at 8. When I go to 0, I'm going to cut down to about 4. When I go to 1, I only get to go to 2. And when I go all the way over to 2, I get to go to 1. And I'm going to turn the paper just so I can graph this a little better. But notice I'm going to always come really, really close to that axis, but I'm never, ever going to touch it. That is part of exponentials. They don't go negative unless there's a negative out front where we would flip them over. The x-axis when we're working with exponentials is going to be an asymptote or something like it. All right, let's take all of this, put it together, and let's see what a word problem looks like. This one's tricky, but bear with me. Pause if you need to go back and hear me say anything again. Take the video as slow as you need to. So in 2000, the population of Phoenix was that many people, and it increased to that many people in 2004. Write an exponential function in this form. This is just our basic form of an exponential that could be used to model the population of Phoenix. And then we're going to write the function in terms of x, which is going to represent the number of years since 2000. Then using our function, we're going to predict the population for the year 2050. Very similar to how I did these last two problems, I just want to organize all of the information in this word problem in something that's a little bit more visual, something easier to kind of parcel apart. So the way I'm going to do this is I'm going to make a table with my years. I know in 2000, the population was that, and by the year 2004, it had increased. So because I know that we're modeling it in terms of x, which is the number of years since 2000, I'm going to create my x, and I'm going to say the years since 2000 to 2000. That's just going to be 0. No years have passed. And in my y, I'm going to put my population. So in 2000, I know it was 1,321,045 people. When 4 years passed since 2000, they had a population of 1,331,391. So how are we then going to create this function that we need? Well, we know that A is the y-intercept. And how is that going to help us? Well, we know that if we are at 0 on our x-axis, then whatever y that goes with it is going to be our y-intercept. So we can right away say y is equal to 1,321,045 people. Now, we don't know our b yet, and we don't know our x yet. Here's how we're going to find those. We have to use our x and our y that it gives us. Notice our function has an empty x and y that aren't being used, and our table has an x and a y that haven't been used. So what we're going to do, I'll change colors here, is we're going to bring those over and plug them in. We're going to say that when we plug these numbers in, so I don't like talking when I'm writing so I don't mess up my numbers. I don't know b, but I do know the x because it's been 4 years since this passed. So now that I have this information, it looks kind of gross, but what I can do is actually solve for b, which is what I need in my original equation. Well, how am I going to do this? I'm going to divide both sides by this really big number on the right. When I do that, I get 1.008 equals b to the fourth. Now, eventually we'll find some really cool formulas that'll help us simplify this easier. But in this case, I'm just going to go into my calculator right now. I'm going to go to math. And right down here, I have this root function that says x here. And what that allows me to, plugged in my answer as my last piece. I'm going to put in the fourth root of 1.008 because that'll take the fourth root of b and the fourth root of 1.008. When I do that, I get an answer of about 1.002. I'm going to switch this out, 1.002. So now that I've done that, I'm going to jump back up to my original function. I'm going to plug this in. How do I do that? Well, y, I still don't know that, equals 1,321,045 people times 1.002 to the x. Notice, I only did all of this so that I could solve down and get my b. Now remember what it asked us for. It asked us to predict the population in Phoenix for the year 2050. So we're going to do that. I'm going to bring in another colored pen. Here's my prediction piece. I'll do it over here. I'm going to plug in 50 for the year X. If I want to know in 2050, I know that 50 years must have passed, and I'm looking for the population. So what does y equal when I plug it in? 1.002 raised to the 50th. We can throw that in a calculator pretty quickly and find that in the year 2050, we are going to have 1,459,835 people. Remember, PEMDAS says we have to take the exponent first and then multiply. Do not multiply these and then take the exponent. You will not get the correct answer. All right, let's flip over to the back. We're going to now define exponential equations. So exponential equations are equations with variable powers, also just known as exponents. I'm going to say EXP exponents. You can read through that quick key concept, but essentially what it says is that if two things have the same base, we know that their exponents have to be equal. And we're going to use that information to solve for things that have variables in their exponents. So again, let's look at some examples of this. Two things have the same base. We know that their exponents have to be equal. And the way that I always show this is a counterexample. There is no way in the world for us to have 2 to the 3 equal anything other than 2 to the 3. If we have 2 to the 4th equals 2 to the 3, we know it's not going to work. So we know their exponents always have to be equal. It's the only way for two things to be equal. So now how do we do this example? Well, all we have to do is say that x plus 1 is equal to 2x plus 3, and then solve accordingly to get what our x needs to be. Excuse me. So I'm going to move the x over. I'm going to move my 3 over, and I get x equals -2. I could easily plug that back in and check. However, I'm going to leave that to you if you would like to do so. This next one's a little bit tricky. We would like to use the property of equality for exponential functions, but we can't quite do it. And why can't we do it quite yet? Because our bases are not the same. Bases must be the same for this to work. In fact, I'm going to go up here and I'm just going to write a quick reminder. Bases must be the same. So that doesn't mean that we can't do this problem. It just means that we have to change the way it looks a little bit before we start solving. And the way we're going to do that, what is another way to write a 4? we could write it as 2 squared. So if we write 2 squared to the x plus 1, we know that we can simplify that exponent. We can simplify it, in fact, to 2x plus 2. And that makes this and this equivalent. Same thing with the 8. I can simplify this to 2 cubed raised to the 2x plus 3, and then simplify that exponent to equal 2 to the 6x plus 9, based on our exponent powers. Now that I have the same bases, I follow the same method I had before. I just say 2x plus 2 equals 6x plus 9. Solve for your x's. I'm going to move the 2x over. I'm going to move the 9 over. I'm going to divide both sides by 4, and I get x equals negative 7 over 4. Just like that. And it's always going to be a little trickier than this original problem. So make sure you're comfortable with rewriting numbers as a different base raised to an exponent. For example, this next one. This one doesn't even really have a base. It just has a fraction on the right side. But let's think of some ways that we could write 1/9. One way that I immediately think of is, why not 1 divided by 3 squared? Now I have a base to work with, and if I want to get rid of the fraction, all I have to do is make my exponent negative, because I know that negative exponents will raise it to the top, or to the numerator. Well, now with this rewritten, I've got 3 to the 2x minus 1 equals 3 to the negative 2. I don't even have to change anything around here. I can immediately just write 2x minus 1 equals negative 2 and solve. Move the 1 over, divide both sides by 2, and I get x equals negative 1/2. I really enjoy doing these. I think they can be really, really quick as long as you see the pattern. The pattern is always just getting the same base, setting the exponents equal, and then doing a little bit of Algebra 1 work, which should be really, really refreshing to us to see that coming back into it. All right, and to just take it one step higher, add just that little last bit of challenge, let's see what these inequalities do. How do inequalities work? Well, first off, we have to be able to have the same base. We still want to use that property of equality for exponential functions, so we still have to find a way to make these bases equal. This one, not as obvious, but 216, 1 over 216, can actually be written as 6 to the negative 3. And I can rewrite the whole thing then as 6 raised to the 2n minus 1 is greater than 6 to the negative 3. I can still just set those equal even though this isn't an equality symbol in the middle. All I have to remember is that I'm putting that inequality symbol in instead of an equal sign. And then I solve the same way I'm used to. Move the 1 over. I get this. Divide both sides by 2. I get negative 1. And then I just do a quick check. Bring back that number line. If I put in anything greater than negative 1, if I put a 0 in here, does it give me a true statement? Well, let's check it out. 2 times 0 is going to be 0 minus 1. So 6 to the negative 1 is going to be 1 over 6. Is 1 over 6 greater than 1 divided by 216? Yeah, it is. So I can do a quick check and find that that is, in fact, a true statement. You don't have to do the check every time, but I would highly suggest it the first few times just to make sure that you didn't miss dividing by a negative. Let's see that again with another one. Same thing here. We just need to rewrite 27 as having a base of 3. I always try to go with the smallest prime base if it's available. So 3 to the n minus 2 is less than or equal to 3 to the third. Prime base, prime base. Set them equal to each other with the inequality sign. Solve, and you get n is less than 5. I do a quick check here. I'm going to circle this, but I do a quick check. Plug in a number. 0 is always my favorite. 3 raised to the negative 2 is going to be 1 over 9, which is clearly a fraction, therefore it's definitely less than 27. So our check does work, and we're good to go. All right, that was a lot for chapter 9.1. If you have any questions, let me know.